All right, so in this final section for our final topic, we're going to talk about finding volumes of solids by slicing. So in our last lesson, we talked about finding the area of a region. So when we talk about a region, that is two-dimensional, and we can therefore find its area. When we refer to a solid, we're talking about something that is three-dimensional, 3D, not 3R, and we can therefore find its volume. So if you look at this rectangular pyramid, if you can imagine slicing it in such a way that we could produce a ton of these rectangular slices. So like if we took a big, I think about like how, if you've ever been at the deli counter, how they slice deli meats, they just kind of like shave them from that, I don't know, it kind of is shaped like a loaf, or cheese if you're a vegetarian and don't want to think about deli meat. If you think about how you could almost like shave this off into tiny rectangular cross sections, that's what we call them in geometry. If we can peel one of them out and look at it over here, this represents a cross section that would be maybe from the middle. We know if we picked one from the top instead, that would be just a smaller rectangle. And if we picked one nearer the base, that would be a much larger rectangle, although the picture I drew looks about the same size. So in geometry, you learned a while back that the formula for volume for something like a cylinder or a prism, for example, is the area of the base times the height, and that capital B is an area. So similar to that, now we learn specific formulas for pyramids and cones that involve 1/3 or 4/3 if we're talking about a sphere. But similar to that, the volume, we can find the volume of this pyramid by finding the area of the slice, and then we're going to integrate the area. So if you look at this slice, this A sub I right here, that represents the area of the ith slice. So A sub I is an area. And then this delta Y is just how tall the slice is. So our volume is going to be the area of this slice times how tall the slice is. But that's just going to give us the volume of a single slice, because even when you get like a really thinly sliced deli meat, for example, let's say it's a perfect circle, it's like a salami or something, even when it's really thinly sliced, it still has volume. So if we want to generalize this and be able to find the volume of solids, we're going to do something very similar to what we did with area. We want to first consider that the volume of the ith slice, that's just what I wrote up there, so that gives us the slice volume. But if we want to figure out the solid, we need to add up all the volumes of the slices. And again, this is a different way of expressing a Riemann sum. So again, this just tells us that we're going to add up from I equals 1 to I equals n all of these slices. And we said that this again represents the volume of a single slice. So then to do this in a way that we can capture all of the volume, the total volume, we need to take the limit. So when we take the limit of a Riemann sum, that is an integral. So I'm going to just go down to this box. So this limit of the Riemann sum piece, this becomes the integral itself. This formula for the volume of the slice, so what was inside of our Riemann sum originally, is now our integrand. And this delta y, in this case, just becomes a dy. So for us to find the precise volume, we need to take infinitely thin slices and add them all up. And that's what that limiting process will allow us to do. And of course, we're going to integrate. So after this video, I'm going to put up a pretty cool applet that's going to correspond with this next example, sort of. We're going to change the example so it does. But if I were to ask you how to find the volume of a solid, what we would say is that we would integrate the area of a cross section, or integrate the area of a slice. So I'm going to just write that down. So the volume of a solid, we're going to integrate the area of a slice. And if you ever go on to take Calc 3, you'll go like really in depth with this with different surfaces. I spent a lot of last summer integrating the area of cross sections.